Welcome back. In this video, we continue our discussion of visualizing surfaces using alternative plots by talking about level curves. Let's recall the previous videos from lesson 7. So far, we saw two techniques to visualize the behavior of the graph of a two-variable function, z equals f of xy. The first one was just a standard surface plot. So we just graphed the surface in R3. And we saw that for explicit functions like this, we could use that plot 3D command in Mathematica. That gives us general layout of the surface, kind of the curvature, what it generally looks like. But we could use a further technique after doing that, which was called graphing the contour curves in R3. So that was analyzing all points on the surface that intersect with a particular plane and then graphing the curve that comes from that intersection. And that's kind of useful information in the sense that those curves tell you all points on the surface that are of the same elevation. You could imagine that geologists absolutely love these type of curves. In fact, we have some in our family and they go nuts for them. In addition to these two techniques, there is a way to visualize the behavior of the surface by actually plotting curves in the domain space. And this technique will be called graphing level curves in R2. Notice this is quite special. Previously on X-Men, the only way we could visualize behavior of a two input, one output function was by mapping into R3. Level curves will be a two-dimensional representation of three-dimensional data. Bum, bum, bum. Very exciting. Let's see what this hubbubaloo is all about. Did I just use that word? Oh my God. Let's never do that again. Okay, so we're going to go ahead and look at the definition of a level curve. We say that in order to graph level curves, we need an explicit function where the output variable z is explicitly written as a function of the two input variables. And we know that this is a two-variable function because if we look at the map, we say that f goes from a domain, which is a subset of R2, into the real numbers. We also define a specific constant z0 in the range of f. This is very, very similar to contour curves. The main difference is that the level curve corresponding to the constant value z0 is the set L of z0 of f, or L associated with z0 of f, is the set of all inputs x, comma, y in the domain such that when you evaluate f at these inputs x, y, you get to z0. I want to highlight something really, really special. This curve that we're going to graph, these end up to be curves in many, many situations. Sometimes they're points, but mostly they're curves. This curve comes from a set of ordered pairs, not a set of ordered triplets. And the way to think about this is that level curves are in R2. Thus, the graphs of these suckers are in R2. Contour curves, in contrast, are in R3. They're sets of ordered triplets. So, just to bring home that point, level curves are subsets of R2 where we're going to actually visualize input values in the domain that produce the associated contour curve C sub z0 of f in R3. So I like to think about these as the pre-image of are contour curves. They're the set of inputs that produce the contour curves. And another way to think about this is to project the contour curves down onto the xy plane, and then to pretend that the xy plane is not in R3, but instead just sits in R2. Let's take a look at what we mean by going back to our famous example, an example that is now spanning 3 videos. If you ever see this as an example on the street, please stop it and get its autograph. It is going to be extremely famous by the end of this video. So we had this function f of x equals 9 minus x squared divided by 4 minus y squared, and we looked at the level curves associated with this. We looked at the contour curves. Now what we're going to do is look at the level curves. So in this case, we had 3 particular z0 values. We had the z0 value of 8. And what we'll see is the moment that I set z equal to z0, this actually gives me 9 minus x squared divided by 4 minus y squared equal to 8. And then, of course, we can do some math. So maybe we bring the 8 over to this side, and then bring the x squared and the y squared over to this side. If you don't mind, I'm going to go ahead and write this in its standard form immediately, and we'll call this 1 squared. Now, what we see is that the contour plot associated with this z8 value is the ellipse centered at 0, 0 with values 2 in the x semi-axis and 1 in the y semi-axis. Similarly, if we had z0 equal to 5, we set this output of this function equal to 5. And then we did some math. We brought 1 over to the other side, etc., to confirm that this would be, oh, maybe I should go a little slow here. This is 4 equal to x squared over 4 plus y squared. And of course, I can bring the 4 over to each side by dividing. So this is x squared divided by 16, y squared divided by 4. And of course, this thing can be written as 4 squared on the bottom and 2 squared on the bottom there. And now I have an ellipse associated with this height. And then finally, we had the constant value z equals 0. And then this would imply 0 equals 9 minus x squared divided by 4 minus y squared. We are now old pros at this. This is x squared divided by 4 plus y squared equal 9. I can divide both ones here. So 4 times 9 is 36. This would be 9. And then we see that this is going to be an ellipse with x semi-axis 6 and y semi-axis 3, which was the same confirmation that we made in previous videos. So we have 3 curves in R2, which we call level curves, that when we project them onto the surface, they create contour curves. Let's go ahead and look at the level curves in Mathematica, and then we'll put those side by side next to the contour curves and see what we can learn. Here we go. Here I am in Mathematica. I've got my 3 contour curves of this graph. What we're going to do now is we're going to actually do a contour plot command, and the contour plot command is going to be through the 3 curves that I just specified. So the first one we said, I think, was going to be the 1 equal x squared divided by 2 squared, and then we are going to add y squared, and then perhaps just for giggles, we'll divide by 1 squared just to make this a little easier. Maybe we should choose, I put brackets around this because I know I'm going to do more than 1. So maybe we should choose the same x and y values as we did in this upper plot, so that when we do these side to side, we're comparing oranges to oranges or apples to apples. What are we doing here? So here we have this thing, and then let's take a look. Okay, notice this contour plot is in R2. 2. And we're going to see this in a second. We're going to call these level curves. So this is what a level curve is. It is the input values that produce the contour curves. Let's go ahead and look at the next one. So I think the next one, which we were going to talk about, was the same style of ellipse. Why don't I be too legit to quit here? Too legit. And write this here. I think this one was 4, and this one was 2. And then we're going to do this in, I believe the next color we did was yellow, right? So here we said that this was yellow. And then I don't know, are we brave today? I'm feeling a little bit brave, considering I've worked some ridiculous number of hours today. I was up at 5. It is now 12:30 a.m. Ah! Okay, so this is 6, and then this is 3. Let's go ahead and close this one. And then the last one, of course, would be green, wouldn't it? So this would be green. Okay, ready? Oh my god, isn't that exciting? So we have this red, yellow, and green. These are what we call level curves. And what I wanted to do is actually combine. Let's go ahead and suppress this detail. So now I'm going to have a graphic called level curves. Up here, we're going to have this called, I don't know what we call this one, surface and contour. Okay, and we'll suppress the show command. So this is kind of doing graphics objects together. And then what we'll do is we'll do what we call a graphics, oh sugar, graphics row. And the graphics row basically allows me to combine two things side to side. And I always forget how this works. I think I go like, I get the surface contour, and then I get the level curves, and I put them right next to each other. It's probably complaining because Mathematica always expect things in lists. Let's see if that, oh yeah, there we go. Do you see it? Okay, let's see if we can get it exactly right on there. There we go. Okay. So you see actually if you looked on the top and the bottom here, excuse me, the left and the right, these are the same images. It's just that on the left image, the contour curves are in R3, and on the right image, I'm only looking at the input values that produce those outputs, which is quite interesting, isn't it? There's something kind of cool that I wanted to show you. Contour plot. So let's do something real quick here. If you put question contour plot and then evaluated this, what you see, sometimes these level curves are called contour lines. I like level curves because it distinguishes between R2 and R3. But what I wanted to show you was, here's the documentation. So the question mark allows you to learn more about this. This is, what do we say? That if you teach a woman how to code, she solves some problems. If you teach a woman how to teach herself how to code, she can solve all problems. I really like that quote. I just made it up a few days ago. Okay, but anyways, if you put question mark and then you have this this command, it actually gives you information about the Mathematica code, and you go into the documentation center. I've spent hours and hours of my time. I've taught myself how to code Mathematica, by the way, and much of that was done in the documentation center. So here you've got contour plot, and then you have the commands, etc. And then these are the level curves, and you'll see this in a second. So let's go ahead and do this. Let's take contour plot, and we'll do it for our particular function that we were looking at. What was this? Well, why don't we just do it? So I won't be lazy. So here is x squared, and then we'll go divided by 2 squared, and then we'll say this is y sugar squared, and we'll say, I think this was just divided by 1, and then we said mine equals what did I do wrong here? Do you remember what I did wrong? Oh yeah, I don't need an equals here. This is a really cool thing. If I just tell what my input and output is, so this is kind of cool. Isn't that amazing? So look at this. These are now the level curves. So what this one here, when I scroll over it, do you see how it says 5? So that's the level curve associated with x equal 5. Or z equal 5, excuse me. Here's the level curve associated with z equals 0. Here's the level curve associated with z equals -5. Here's the level curve associated with z equal 10. So Mathematica automatically produces it if I don't give it a truth value. And then I also wanted to show you there is a way that you can specifically tell Mathematica which contours you want. And let's see if I can remember how to do that. And by remember how to do it, it means I'm literally going to look on the documentation center. Let's see. Oh yeah, so this is one way to actually physically say this is the one contour that I want to do. Kind of gets ugly real quick. I'm going to stop here. You can get lost in documentation, or I can anyways. So let's go ahead and delete this cell. Gets me back here. So anyways, this is a really cool way to graph level curves without specifically graphing each one individually. And then up here we saw a way to combine all three together in a single contour plot and then use the row command. Alright, I'm going to be quiet now, and we'll see you in the next video where we do some calculus from 1A on stuff you've seen here. Really exciting stuff. See you in the next video.